Thank you. So this is about universes and how to elaborate them and work with them in type theory. And this is joint work with Marc Bezem, which lives in Norway, not Finland. So the outline, I'm going to do a small recap on universes in type theory, the typing and elaboration, and then talk about a solution to mix algebraic universes with polymorphic and cumulative type theory in the rock proof assistant. So as you probably all know, system U is inconsistent. So if type has type, then we can derive inconsistencies and paradoxes. So we use hierarchies of universes indexed by natural numbers to ensure consistency. The introduction rule for the universe, predicative universe, UI lives in UI plus 1. And we also have closure under dependent products, where we take the max of the domain in the codomain. And usually we also have a bottom universe, which we call U0 or set in rock. When we look at the algebra of universes, so we have this bottom universe, successor, and max. But usually when you do polymorphism, we also have a notion of variables that can be substituted by arbitrary expressions. And we have some algebraic laws to follow. 0 is neutral for max, successor distribute on max. Max is important, associative, commutative, and subsumptive in the sense that max U plus 1 should be equal to U plus 1 in your theory. And when you're doing elaboration, you have another kind of variables that appear, which are meta variables that you want to solve for, that are not, part of the term that were not written by the user that you would like to infer. But you have to be careful that this theory is non-unitary in the sense that it has no most general unifiers in general, so you could get into stuck constraints in practice. And this happens in Agda only, for example. Rock has a slightly different system where we also have a cumulative hierarchy of universes. So UI is included in UI plus 1. And this goes to the right-hand side of to the codomain of products as well. So a product ending in UI is a subtype of one ending in UJ for I less than J. And so when we add polymorphism plus commutativity, we get bounded quantification on the universe variables, which was already studied in the 90s by Harper and Pollack, and which we implemented in Rock with Nicolas Tabarot in 2014. This is the kind of definitions that you can write. You can quantify on universes I and J and some constraint on them, and then type check the term subject to this constraint. So you need to do some kind of consistency check when you add a constraint. And the theory is basically this. You need to check entailments where you have some inequalities between universes and you must show an inequality holds. Or that there is an inconsistency, and then it means that there is no valuation of the universes in natural numbers and you have an inconsistency. The previous type inference algorithm of Rock was actually slightly refined so that it did not handle all the possible constraints in this algebra. So you didn't get general constraint between two universes, but a universe on the left and the variable on the right. And through careful study of the type inference algorithm of Rock, we could ensure this property that we only generate this kind of constraint. So the problem with this is that then max expressions can only appear kind of on the right of your typing judgment, and they cannot be put back in terms directly. You need a kind of freshening operation. A typical simple example, I type the identity function. I don't give the type of the carrier, but I just give the argument type 0, which has type 0 plus 1. But as this is an algebraic expression, I cannot put it back in the term, so I need to freshen it, introduce a new meta variable I, and a constraint that I is greater than 0, and this is well-typed term now. So the pros for this system was that it was possible to do efficient entailment checking with a state-of-the-art algorithm by Bender and Tardon. The problem is that we have a restricted algebra, very error-prone API, so when users infer the type of some expression and want to put it in some application, for example, when you're doing metaprogramming, that's something you do all the time, you have to remember to freshen your things and to add constraints. So that was very error-prone. And of course, it also generates a lot of fresh levels. Each time you have an algebraic expression, you need to hide it behind a fresh variable. So the solution is proposed is to handle all this algebraic universes algebra in this polymorphic cumulative type theory, and we'll see how variances help doing that. So our new implementation of universe checking is based on an algorithm by Bezem and Cocker. that was introduced in this paper, loop checking as an uniform world problem for joint semi-lattices with an inflationary endomorphism, which in layman terms just means that we can decide the attainment for the max less than and plus theory in polynomial time. So they don't really give an algorithm, they give a constructive proof, and we had to kind of extract the algorithm, thanks to the help of Marc, to actually write a low-kernel program that's part of the rock kernel now, or that will be part of the rock kernel, that does loop checking and entailment checking based on these ideas. So I won't have time to enter much into the details, but basically the idea is to encode constraints into a set of horn clauses and maintain a model of the variables in the natural numbers plus infinity, where infinity will actually denote a loop, a level that should grow infinity often. Okay, so we extracted this algorithm and improved it a little bit by adding an optimization that was already part of the previous algorithm, when semantically to a level and L and some expression L prime plus K are equal. We represent that by a substitution, really. So L is represented by L prime plus K in an algorithm. And then you can check equality of simple expressions in constant time. That's really useful for efficiency. We have termination correctness and work in progress completeness proof of the our implementation of the algorithm in work. And then this generalizes indeed the system to handle all constraints, greatly simplifying the API, avoiding the proliferation of fresh questioning of levels. But still, when we have cumulativity and inverse polymorphism, we still generate a lot of constraints that would not appear if we didn't have cumulativity. So again, I'm applying the polymorphic identity here to natural numbers and the zero natural number. And this will generate a constraint due to the subtyping rule on application that my meta variable I is greater or equal to 0, rather than just setting it equal to 0. But we can see that without loss of generality, we can actually set this variable to 0 without changing the principal type of the application, and without changing the convertibility behavior of this expression, because both ID at the meta variable I and ID at 0 reduce to the same term, so they're convertible. So to do that in a sound way, we will need to record how, where and how the bound universes or the meta variables appear in a definition to perform sound simplifications like this one. So we have a notion of variance that we will record for every bound and meta variable in our term. So variances can be irrelevant if the universe does not appear or appear only in other irrelevant places, covariant, cotrovariant, or invariant. So this is a notion that is already part of ROC. That's part of the notion of cumulative inductive types. So here I'm showing you the definition of equality, polymorphic definition of equality, which binds a single universe I as a first binder for the carrier of the equality, which mentions I and mentions I again in the conclusion. Here, our notion of variance is that it is contravariant. It appears contravariantly in the first binder. We went to the left of an arrow. It's covariant in the type, in the conclusion of the inductive, but it does not appear in the constructor arguments, so we are going to say it's irrelevant there. We have shown with Timani that this allows us to treat the universe I as irrelevant as soon as EQ is applied to its first parameter, because we're basically removing this contravariant occurrence. And we can show through a set theoretical model that indeed we can validate this kind of rules. Let's say that equality on natural numbers, when it's fully applied like this, this is a conversion that holds for any I and j, as long as, of course, as the expressions are well typed. And this is kind of the justification also of the so-called template polymorphic inductive types in ROC. So our idea here will be to lift this analysis to all the definitions, not just inductive ones. So typically, for this definition of a relation, so a relation on a type A is a binary predicate on A. We will see that the A binder here is considered irrelevant as soon as we are applied to the first parameter. So again, this is due to the fact that we are not changing the principal type of the expression, and convertibility still holds for any instantiations of I. Here, I have a convertibility of all the applications to A. And you can think of the justification also being that you can compare the two parameters. So here they are the same, A and A prime. But when you're doing first order unification of the constant, you're basically comparing the argument at the maximum of I and J, because this universe was in a contrarian position. Okay, so this is compositional. So you can compute the variances for the definition of proper here, which is just a reflexivity proof of the relation, compositionally by looking at the variances for each constant that appears in the definition. So in this case, for proper and respectful here, which is just lifting relations on arrows, all the arguments all the universe binders are basically irrelevant as soon as the constants are sufficiently applied. So this gives us a sound way to do first order unification by postponing the comparison of universes when they are not necessary. Sometimes they are still necessary if the universe is invariant or covariant. But it also enables simplifications. We can see that the I binders here, or I and J binders here, can be lowered to recover what we would have without cumulativity and without losing any generality. So typically, function of containers will have irrelevant binders as soon, again, as they are applied to the parameters. So here you have the mapping function on list. We can see that I is irrelevant in this case. When you have list applied to some A, the universe annotation is just here for typing reasons, but there's no functional content, so it's irrelevant. If you look at how the groupoid laws are defined, you can see that actually they are the universe binder for the carrier type of your equalities or iterated equalities is always irrelevant, which makes sense that groupoid laws work at any universe level. Nothing depends on the specific universe level. Finally, on the side of the user interface, how do you interact with the system? So you can choose to declare only the quantified universes, and that's really the mode that we'd like to push for users to use in the system. So here it checks that no invariant or covariant universes was missed in the annotation in the type. So the type is really mentioning only I and J and no hidden universes. All these hidden universes have been simplified so that they are expressible in terms of I and J. And at the end of a proof, we try to solve all the meta variables in terms of the universes that you have found. In practice, what I have seen when developing or porting the hot library is that indeed it's pretty rare that the simplification is not able to simplify in terms of the universes you have got. And there's also a full checking mode where you can say precisely what constraints should hold on the bound universes. And Rock will check at each time you apply a tactic or do a unification or type checking that indeed you are not relying on any extra constraints than the ones that you have declared. And this can allow you to work finely with cumulativity. So there are examples in the hot library where you need really fine-grained relations on universes where you can use that. So porting the hot library to this new system is not that big of an effort. It's about a 500-line change. Mainly adding explicit universe bindings and changing some instances that have changed due to the ability to have max universes. Usually the polymorphic definitions take less universes as arguments because we don't have these proxy universes representing max expressions. Okay. So to summarize, we use Bezem and Kokan's algorithm for full universe inference and checking with algebraic universes and cumulativity. We can use variances for sound and efficient conversion, unification, and minimization. And it supports both explicit and implicit universes and constraints in work. The work in progress, we want to complete the formal proof of the loop checking algorithm and continue porting reg developments. This has been done for hot. The next big step is to update the mathematical components library to not just adapt to the new algorithm, but also also make it universe polymorphic because it is not, it has not done so today. And there's pull request on Marc following this development. Thank you.